So, welcome today to our Richard L. Thompson lecture series, where we're going through Sariputa's books, covering them chapter by chapter, getting some summaries of the contents and highlights, and then there's a short discussion to follow the summary. So 2 weeks ago, we had Krishna Kripa. He presented on chapter 5, the empirical case for the Vedic world system. And today our presentation is by Doug Watson, Chapter 6, Modern Astrophysics and the Vedic Perspective. So thank you very much, Doug. Welcome. Doug Watson works as a data scientist for a small tech company based in Pasadena, California, and was a National Science Foundation postdoctoral fellow at the University of Chicago Kavli Institute for Cosmological Physics. He received his PhD in physics from Vanderbilt University with a specialization in the field of theoretical astrophysics and is serving as chairman for the November BIHS Vedic Cosmology Conference. Thank you, Doug. And go ahead.
Take it away.
Take it away.
Okay. Thank you for inviting me to do this. It's a really great honor to speak about Sariputa's work. And hopefully my background as cosmologist can help maybe bring some more modern topics in astronomy and cosmology into this chapter 6. I'm really excited to give this talk, especially because I've given many talks in universities and other settings, and this is the only place I hear with that feedback. So this is nice and comfortable and very relaxed. Okay, so up until chapter 6, this has all been about constructing a theory that's solely based on sense perception. So that's what we do in modern astronomy and cosmology. And as Sariputa says, the maturation of astronomy and physics nowadays seemingly towers over ancient, what he says, static ideas. And I think what he means by that is not that there were no dynamics in the picture of Vedic astronomy back then, rather that there is a picture, say 5,000 years ago or so, that doesn't change over time. And we all know that Sariputa loved mathematics, and I would agree that the language of math is extremely beautiful, but it's ultimately limited in its scope if we want to find a totally comprehensive and, as he puts it, a new sophisticated framework. So one answer to this challenge, that the Vedic cosmology is no match for our grand picture in modern cosmology, is a matter of what the purpose is. So to appreciate Vedic cosmology, you have to understand, the teleology, the purpose behind it, and the basic tenets on which it's based. So first, he says to elevate one's consciousness, and then it applies to practical methods of dealing with the motions of planets as they apply to daily life. There's also astrological, ceremonial forecasting, and fulfillment of needs with regard to higher aspects of reality. So quite a different purpose from that of modern cosmology. So in that framework, you don't need any real rigorous math, but either way, the nature of reality cannot be understood simply by relying only on the senses. In fact, if we just want something that's based on the senses only, then it could be agreed that modern cosmology is in fact superior to Vedic cosmology in that way. But we can tell that a higher dimensional construct is required. So let's do that. Let's construct a new cosmology based on Sariputa's vision. And he starts off with a great thought experiment. This is the idea, the principle of relativity and planetary motion, not Einstein's relativity or anything like that, a different kind of more simple principle of relativity. And you'll see where this is going and why he sets it up like this. So in physics, you can have just two objects and you have some equations that tell you how these objects evolve with time. It's calculus, pretty simple and straightforward. So imagine you have two objects, A and B, just these two, and they're approaching each other at a constant velocity. From where we're standing, our perspective, we can see them moving together. But if you just look at the equations alone, how they unfold, if you were B, it would seem like you're standing still and A is approaching you. If you're A, you'll feel like you're sitting still and B is approaching you. So you start to get this idea of relative motion. Okay, but what about rotation? Rotation causes a centrifugal force. So this is the force where, if you take a hard turn with your car to the left, you fall to the right. That's basically a rotational force that you can feel and measure. And that's something that you can do. There's not really a relative situation about this. It's just rotation. But Ernst Mach in the 1800s came up with a very interesting thought about this. He said, imagine if these two objects are the same mass and they're the only two things in the universe. Could you actually measure centrifugal force? How would you know which one's rotating if they're the only two objects and they're the same mass? You can't. It's an interesting thought experiment. So this is what Sadaputta goes on, as you can see where this is headed for our Vedic astronomy. If this idea of relativity of motion is granted, one can then argue that the geocentric or heliocentric viewpoints stand on the same footing physically, and we can choose one or the other depending on what's convenient that we want to explain. Obviously, as we just saw, this is a non-trivial point and pretty fascinating that that was understood back then. In the case of the astronomical Siddhantas, one can argue that the geocentric viewpoint is simply the more practical of the two, since all computations must ultimately be expressed in geocentric terms. And if we intuitively prefer to think of larger masses as stationary, again, which is intuitive, and small masses as moving, rather than the other way around, then we will prefer the heliocentric view. So in other words, you can use both of these strategies within the Vedic astronomy framework. So how does the Bhagavatam picture look? Well, it's mind-bending to say the least. So one, we have Bhumandala, which is located in the plane of the ecliptic, and therefore Bhumandala must also rotate daily with the Kala Chakra. Second point, the movement of the sun in Bhumandala consists of one leftward revolution around Mount Sumeru per year, and both Bhumandala, the sun, and the other planets are carried in one rightward rotation per day by the Pravaha wind. Okay, got this so far. From the perspective of relative motion, which we're talking about, one can regard the Earth as rotating and the stars, Pravaha atmosphere, in the Bhumandala as stationary. Okay, in that picture, the sun is then seen to rotate with respect to Bhumandala, being carried by its chariot. From perspective that larger masses should be viewed as stationary, it's reasonable to regard the sun as moving and Bhumandala as stationary, since Bhumandala is much greater than the sun. Okay, what about the universal shells? Considering the covering shells of the universe and the Pravaha wind is blowing with respect to these fixed coverings, it then makes sense to suppose that the Pravaha wind and various celestial bodies are moving with respect to the universal covering, since the coverings are more massive than the celestial bodies. Again, we're seeing like layers and layers of how perspective matters when we're trying to construct this framework. So conversely, in this picture, it also makes sense to suppose that the sun is moving with respect to the mandala. And there are some good metaphors in the body for this kind of idea of relative motion. Okay, so the picture moves on now to the next subtopic, which is gravitation. So we're going to go basically from Newton to Einstein back to the Bhagavatam. And Sadaputta says, Srila Prabhupada has pointed out that according to the Vedic understanding, planets float in outer space by the manipulation of air. Srimad Bhagavatam 5.23.3. He has rejected the idea of gravitation, calling it an imaginary law, but he has also said that the visible effects produced by the real causes of planetary motion can be called gravitation if one so desires. Okay, so let's talk about the modern state of affairs, and hopefully I can help advance what happened when this book was published in 1989 to the picture we have today. So back in the mid 70s, an astronomer named Vera Rubin made a pretty amazing discovery. So what I'm going to show you here are two galaxies, kind of like our own Milky Way galaxies. They have these spiral arms and they rotate. We observe this in our own galaxy and galaxies outside of our own. On the left side, this is basically what you would see if you were kind of rotating like a record player. You see this little graph at the bottom? It's got the speed of rotation as you move out from the center of the galaxy. So you can imagine with a record or with our solar system, let's take our solar system. Mercury is spinning around the sun because it's really close at a fast velocity. Jupiter and the outer planets are sort of going more slowly around. That's how a record player works. But when she made observations of galaxies outside of our own, she noticed a very interesting thing. As you move farther and farther away from the center of a galaxy, the speed of rotation actually doesn't go down, it stays the same. And according to Newton, that basically means there's some extra mass that we're not accounting for. So nowadays, you may have heard of it. This is the sort of first signals of dark matter. Dark matter is, well, we don't know, but the basic idea is that it interacts only with observable matter through gravity. So we can't see it, we can only observe its behavior. And there have been a lot of additional observations that sort of confirm this behavior, but we still have no idea what it is. And there are also alternative explanations to what could be causing it. Yeah.
Question for you.
Sure.
So does that suggest that the animation of the galaxy on the left is sloped down like a coin drop game, and the left one is flat, or is there no difference?
No. It's just saying that so the galaxy is basically in a disk, and it's just spinning, and will stay at that rotation, sort of in equilibrium, just spinning. The same way a record would just keep going forever if there were no friction. The one on the outside is just saying it's the equivalent of putting maybe some pennies at the outside of the record, and it starts all going at the same pace. Doesn't matter. There's some more mass there. Good question. Okay, so this was a realization I had yesterday, is that this book was published in 1989, and that's kind of actually a pivotal year in cosmology, is how it would start to change to the picture we have now, some decades later. So there would be a real shift in the modern cosmological paradigm, kind of starting around this year. And I'll go through this quickly to not get too confusing, but the standard picture of the Big Bang is that you have some sort of event that started off as an initial hot, dense plasma that sort of, let's say, exploded in all directions. Okay. And from that, there's expected to be sort of in every direction a relic of that explosion. And you can measure that a couple ways. So you can measure it from light. In this case, it's called the cosmic microwave background. So in every direction, if you look around in the sky, we have the exact same microwave detection everywhere we look. And that is associated with a temperature. Any sort of light beam or anything has an energy associated with it, and therefore a temperature. So this is a temperature map of the baby universe, essentially. Now, this mission, it's called the COBE mission, was launched in 1989 as a satellite, and then data first received in 1992, and subsequent Nobel Prize for this, because one of the predictions of the Big Bang Theory is that if you look at this, it would be totally smooth, but what we're doing is really honing on very tiny fluctuations in temperature, very, very subtle temperature differences. So it's not completely smooth. There are little overdensities in temperature across the universe. And this is considered to be about 300,000 years after the Big Bang event. And ultimately, those little inhomogeneities are overdensities of matter, and those will eventually sort of clump together due to gravity and form all the structures we see today, like stars and galaxies. If there weren't those slight fluctuations, there would be nothing. There would be no accumulation of any structure in the universe. So this was a surprising and remarkable success for modern cosmology. And now these have advanced to more and more sensitive satellites, as you can see, and just sort of pinning down the success of this model. But don't worry, it has many, many flaws. Um, we'll get there. This is not, this is just a fun cartoon example. It's not a linear scale. It's just showing as you go back to some singular event, perhaps, let's just call it the Big Bang. Right after that, that little blue piece is that cosmic microwave background. That's the sort of fossil relic of the beginning of the universe. And then the universe sort of marches along in time and doesn't do anything very interesting for quite a while. It's pretty boring. But then eventually you start to get proto-galaxies forming and little structures forming. And then at about half the age of the universe, which is not depicted in this diagram, something really interesting happens, which we've only known about for about 2 decades, was that the expansion of the universe, it starts to speed up, it starts to accelerate. And that's what we dub dark energy. We don't know what it is. We have ideas. We just know that its behavior is causing the expansion to accelerate, perhaps infinitely on forever. So this is what the universe is made of in the picture nowadays, which is quite different than how it looked in 1989. So if we look at a literal pie chart of what makes up the universe, the visible matter like this and all of us in here and everything we see is a measly roughly 5% of the contents of the universe. Dark matter is expected to make up around 27% of the rest of the matter budget. And then dark energy, that energy density is about 70% of the universe. So 95% of the universe is dark to us and we don't know what it's doing. So take that, modern cosmology. There's more to this story, though, and allow me to elaborate a little bit on this. My wife and I have a farm, and we have animals that fight all the time. And this made me think of the main issue with what's going on, as some of you may know with modern cosmology, is that we have Einstein on one side, who has his theory of gravity, which is remarkably successful, unbelievably. It's how our GPS works, everything, how we understand cosmology from start to finish. And that operates on larger scales. Then the cat on the right side is representing quantum mechanics, which is our by far most successful theory in physics to date. It's essentially capable of describing to an unbelievably number of decimal places accuracy of all physics on subatomic scales. But these two don't like each other. It's a problem. So hopefully my drawings, I like to draw, it helps me, but I don't know if it helps you guys. Here we go. So here's a thought experiment, because often people hear, I heard that Einstein and quantum mechanics don't like each other. What does that mean? It's basically, think of this thought experiment. So say you take a section of space, anywhere in space, and you want to zoom in and understand what it is on the most simplest fundamental level. So I give you this giant magnifying glass, and you peer into it, and you peer into it. Well, to observe anything, we need light, right? And the smaller you want to probe, the higher the energy you need. That's why we have these huge particle colliders, the biggest machines we've ever made, that are trying to look at the smallest things in the universe. So it takes a lot of energy to understand what space is doing at small scales. And the conundrum is, let's say you try and do this, and you try and look at space on small scales. Eventually, you'll hit such an energy level that you'll create a black hole and you can't do your study because you've created so much energy that it will collapse on itself. So Einstein equals mc squared is all you really need to know. And there's our intrepid scientist falling into his own experiment. So if the point is, if you think of our universe here, where it started from some incredibly hot, dense, small event, and then evolved with time to expand, if you rewind the clock backwards with this theory, well, gravity and quantum mechanics, what do they do at that point? If they don't get along, there's a problem with their theory. And cosmologists are very good at skirting around these ideas. I mean, they are looking for some compatibility or new theories, but what is most often quoted is that talking about what happened before the Big Bang is meaningless. And I'll give you an example. This is a famous another thought experiment from Stephen Hawking. He said, imagine, Maharaj, you and I are going on the globe. We're headed to the North Pole in opposite directions. We both get to the North Pole. You get there first. I come and meet you. And I go, hey, which way is north? And you're like, that's a meaningless question. It doesn't make any sense. We're at the North Pole. And that is literally like the argument that's often made for why asking anything that could happen before the Big Bang or cause the universe is a meaningless question. Yeah.
Is that because time didn't exist? Is that the reason given?
The reason is that, yeah, time and space are created from well, non-technically speaking, just from this event, space and time are manifested from it.
Question.
Yeah.
Do they acknowledge that if there's no time or space, and since then the Big Bang couldn't take place in time or space, that how does something happen outside of time and space? Do they worry about that?
Well, that's the philosophical problem, right? It's almost I would say it's almost pseudo-religious to think that you could just get this from some, what they would say, some empty vacuum. Or where did the vacuum come from? You know, how do you, it's a dead end. So again, this is my favorite opportunity to bring forth a more comprehensive framework based on something more fundamental than just physicalism. So not a huge deal. It's just to say that there are alternatives to gravity other than Einstein's views, and some would be very intriguing to scientists of the BI that I could talk about after if anyone's interested. Yeah,
Quick question, going back to your pie graph
sure.
about the 5% of matter that we can comprehend. If we can only comprehend 5% of matter, then how do we know that there's a 95% that we can't comprehend or can't see?
Well, I'll try and state it a different way. It depends on what you mean by comprehend. We can study its behavior. We know what it's doing to visible matter, but we don't know what the thing is itself that's doing it. So all you know is its behavior. So for example, the universe is expanding, and then for some reason that expansion speeds up. We don't know exactly what causes that. You just observe the effect. So yeah, that's the idea. We don't know what it is, dark energy or dark matter. We just know its effect on visible matter.
And so where do the percentages come from?
Those come so when you evolve, let me go to this picture. So this is the name of the game in cosmology. We can't see evolution over billions of years. All you can do is basically get high-powered telescopes to take snapshots at different points in time, right? So you take different snapshots, and then from that and some assumptions, specifically using some of Einstein's equations, you make an evolutionary model from that. You make logical assumptions about how you could go from there to all the galaxies we see today. So in that, Einstein's equations are governed by the matter content of the universe, the pressure that's expanding it. All these things are variables that are constrained by these observations we make. So it's the observations themselves that told us that the universe was expanding and then rapidly expanding.
And then the percentages.
They just fall out of those equations because they have different impacts on how
So in other words,
observable works.
so you would need a certain percentage to get observable effects.
Yes, correct. So if the dark energy percentage in your model was 30%, the output of that would not look anything like the universe we observe now.
Christy had a question.
No, he answered.
There's a cool simulator online that lets you like change
Yeah,
the sliders
yeah.
of dark
Yeah.
matter, dark energy,
Yeah,
and
yeah.
dark matter, and tells you what would happen in that universe. It's
Yeah.
pretty neat.
Okay. So finally, as Sadaputta says, there's the question of how a theory of gravitation should deal with the matter composing the invisible realms of the universe, including Bhumandala. And here we confront our almost total lack of knowledge of the physics of higher dimensional material domains. Indeed. Okay, space travel. I'm not going to talk too much about this, but I love what he has to say about it. So the Vedic literature contains a lot of references of ideas of traveling to different planets. And for some beings, like great yogis, demigods, it is possible to travel from one part of the universe to another by direct use of mystic cities. No machines required in this ability. The empowered being is able to transcend the constraints of ordinary space and time. However, machines are also used for interplanetary travel, and it would seem that many beings who are capable of traveling through space on their own also customarily make use of such machines. This may have been known to you guys, but not to me. It does seem, however, that flight to other planets is sometimes possible for human beings during the Kali Yuga. In Bhagavatam 2.737, when the atheists, after being well versed in the Vedic scientific knowledge, annihilate inhabitants of different planets, flying unseen in the sky on well-built rockets prepared by the great scientist Maya, the Lord will bewilder their minds by dressing himself attractively as Buddha, and will preach on sub-religious principles.
Do we have a Bhagavatam here so I can check the Sanskrit? Because that would be a non-literal.
I hope we do.
Maybe the library.
It's like there's a bunch up here.
Yeah.
I see them right here.
Okay.
She's getting them in order.
Okay.
We need a professional basketball player.
But this was I didn't know that maybe
So-
knowledge to everyone is that Jiva Goswami says that this refers to a different Kali Yuga.
Are you quoting Siddhartha?
Yes, those aren't italicized is not me.
Because if I remember correctly, that's not a literal. Can I just take 1 second here?
Yeah, it'd be good to know.
They will be shown. Okay, the key word, I think we have actually actually it's up in my room, Sanskrit dictionary. So the word which Prabhupada translates as rockets is pur V.
Word V.
Pur, P long UR, and then V, instrumental plural, which have been constructed, arranged by Maya, not Maya, along with it, sort of the celestial wizard. Adrisha Turbi, which says unseen in the sky. Lokang Tam, and so then, yeah, it's not rockets. It's an interesting translation, but I don't want to interrupt you. So what I'll do is I can
Here,
what's that?
O'Neill Williams.
Oh, yeah, it's what I could do is I could send you or send everybody sort of a very literal I suspect that's compound for poor. Okay, good. Found yes. It's actually the word poor. Where consonants becomes a long U. So as in so poor V means in abundance, abundantly. So the word that Prabhupada translates as by rockets, the BHIH just means instrumental plural, like by plural, some things. And so what Prabhupada translates it by rockets actually literally just means abundantly.
Like word, like full, right? Some kind of
Yeah.
completeness.
So it's not, and it also, but okay, it can also mean a rampart, wall, stronghold, fortress, castle, city, town. And so that would be something military, right? A fortress. So it could be by fortresses, but the fact that those fortresses are flying fortresses, and then Adrisha Turbi, which Prabhupada translates unseen in the skies. Let me just get the tour quickly.
Who had the flying city? Was that Cardano movie?
A
Yeah.
lot of the Shiva, the Tripurari, which fights the demons in flying fortresses.
Nice.
It's actually used. And that's
Which is kind of like a rocket.
yeah, it's not like rockets we have.
Right.
So it's
Not
a little
about NASA rockets.
not NASA rockets. But
I'm translating this.
Or maybe they are.
19th, second until
Yeah.
1970.
Yeah.
Before that.
yeah, before that.
Exactly the point.
Should I move on? And
Just in response to that, Krishna addresses himself in an attractive form as Buddha, somehow in response to those rockets. So, but yeah, we'll talk. Maybe
Okay.
later we can talk about that.
Yeah.
Sorry. Just to note though, whenever you're using like a translation from our books, caution, because there's a lot of non-literal translation in our books,
Yeah.
and so for scientific or academic purposes, you always have to see what does the Sanskrit actually say.
There's also a lot of commentaries that you can look at, and
Yeah,
people have already kind of thought about it, and it's good to know that at least. Maybe not accept it, but like,
Yeah, there's a huge tradition here. I mean, when we reference our books, we just reference our books. That's what we're doing.
Yeah.
And then acknowledging that there's all this other stuff too.
Yeah. Okay, the next subtopic is the universal globe and beyond. Let me know if I need to speed things up, how we're doing on time, or if I have just unlimited access. Okay. So this is a slight aside on my part because I think it's important for everyone in the room and everyone listening when we talk about modern cosmology and science in general. And Stethity is kind of an expert on this too, is that you have to, and this is something I was never taught in undergrad or grad school or anything like that, is that you have to be aware and always keep in the back of your mind the axioms and assumptions going in to even starting the endeavor of modern cosmology. So all physical models in physics are causal models. And they're pretty straightforward for things like stars and galaxies, objects. You can just study, apply your physics to that and do that. But cosmology is looking at the entire universe. So things get a little tricky there. And this can really stretch the limits of what your assumptions going in to physics are. And in that regard, any causal model has its own domain of validity. We have a tendency to stretch beyond that, and I'll talk about that a little bit more. But it should be stated clearly, which it never is, and not exceeded. And I'm not doing this to be antagonistic. I'm just saying from my own experience that was I never stated that clearly. It's just you do your work and you think you've discovered stuff that's reality. So we'll be able to use testable physics up to some point, but after that, especially when I was talking about something like Big Bang cosmology and cosmogenesis, you're pushing into the domain of speculation. I can talk about many other examples about fundamental assumptions that go into these things and the axioms used. I would say Sariputta, if I had to guess, was so aware of these things because he was a mathematician, and they are much better at acknowledging axioms and what they rely on. So what are the limits of testability for causal models? In one way, it almost doesn't matter because they're just that. They're models. They describe reality, but we shouldn't confuse them with reality, which is 100% the trap. I'm just using myself as the model here that would confuse it in that way. You have some observation, you have your model you just came up with, you're so excited, it matches all the observations. You think you've just discovered the reality of the cosmos. But it's just a model based on assumptions. So I need to expand on this just a little bit more. Stick with me here. So this idea of underdeterminism and the restrictions of observational data, because cosmology is just using telescopes to observe things out in the universe. So we're relating knowledge to an external reality. So we want to test our models against what is actually out there by experimental means. But the data are inherently restricted. And I'll tell you why that is. There are basically three main reasons. One is we depend on the cosmic speed limit, which is Einstein's speed of light, which is non-varying. It's just the constant c. That is an assumption that we take from the start and never deviate from. And if that's true, if we take that true, that there's a fundamental speed limit to the universe, then that means if you start with some sort of Big Bang, light will be expanding outward, and it can only travel at a constant speed. And then as the universe expands, we'll be traveling at that constant speed. And that will set sort of a distance limit for how far you can see. So we have a fundamental, what's called an observable horizon, which we can't see beyond because light hasn't traveled far enough for us to see. That's our only tool is light.
So as the universe expands, that doesn't change, it accelerates, it doesn't change the speed of light.
Doesn't change the speed of light. Light goes along for the ride. It actually stretches, but it doesn't change the speed, it just changes the wavelength. Speed is always constant.
And let me just
Yeah,
clarify, that's because that if it went because of E equals mc squared.
well, the C is
Yeah, it's light. Yeah,
It's
but
light.
but if it went faster than that, then we lose our definition of mass.
correct. So that's
Yeah.
it's a great example of E equals mc squared. We test it all over the place. We bomb countries with it. It works, but then you're taking that and saying that it's constant everywhere in the universe.
Yeah.
Well, how would you know that? But if your model starts from a singular event, then it would make sense that it's constant everywhere if everything started from the same place. But you can see kind of the tautology there,
Yeah.
the assumption that goes in, and you're confirming that assumption. And then there's an actual physics horizon. So there's only a certain energy scale we can probe down to, and then we're stuck. So you can't really probe. It's a fundamental limit. We actually cannot go beyond it, as far as we know in physics. So you can't answer questions about what happens before a certain time in the universe. And then on the ontological side, if we take, or we should take, selection and detection effects into account. So what is there that we can't see? What don't we detect? And these are crucial in determining what we actually see and measure. Again, there are things we don't see that we infer their behavior from. But again, the universe is unfathomably vast, so we can't assume that we know what's going on in every corner of the universe. So in how I'm saying this is philosophy is inevitable in the study of cosmology, and I would argue even in purely physical cosmology. And our models are underdetermined by observations. So we make models and we extend them beyond what is allowed within those model parameters. So even with as much data as you like, and you can change your cosmological model as much as you like, you still have to interpret the model. And that's a whole nother step. And we'll gloss over the fine-tuning stuff for now. In Vedic cosmology, the material world is not assumed to be made of the same nature in all places, and space is not postulated as an absolute background with which in all phenomena take place. This is another really cool thing that wasn't really in play when this book was written, and even earlier in the earlier 2000s. So I think many modern physicists would agree that space is not actually fundamental in physics. It's not a background within which all these objects play around in. There's something more fundamental to reality. So there's some agreement on this new aspect that I don't think has been considered before, where modern physics and cosmology has some agreement with Vedic cosmology in terms of space. So in Vedic cosmology, material space or ether is generated at a certain phase in the process of creation. Again, this is analogous to what we're starting to understand in physics. and takes place only in certain bounded domains, Brahmandas. So Prabhupada has spoken of these domains as universes, and that gives a new meaning to the English word.
Question.
Yeah.
If you don't mind. The concept of ether, which was for a long time disproven,
Yeah.
but now with the Higgs field, it looks like an ether.
I don't know how you would, it depends on your definition of
Yeah.
ether.
Yeah, because it's everywhere. It's everywhere and gives a rise.
Well,
to
there are
matter.
fields everywhere. So, for instance,
Yeah.
temperature is a scalar field. You can stick a thermometer anywhere in the universe, and you
Okay.
can measure temperature.
But I think
They had a concept they identified there in the late 1900s.
Yes.
That concept was
Early
not
1900s.
considered viable,
Yeah.
but it was a definition stuck to the word ether.
Yeah.
So, what is Vedic definition?
well, that's the real point, because whenever you see ether in our books as a translation of a Sanskrit word, it's not referring to a substance. I mean, it's referring to space. It actually means, the Sanskrit word always means space. And I think the Bhagavatam and Sankhya specifically says that space doesn't interact. Krishna says that in the Gita, chapter 9. So we're not talking about some material thing that interacts with other material things. In fact, the ether or space is always given in analogies. Krishna used an analogy as an example of something that doesn't interact. So, for example, Krishna is trying to explain that all things are in me, but I'm not physically interacting with them. And he gives the example of space. Again, you can translate it ether, but he doesn't mean the 19th. I mean, Steve, did you know about this?
There was ancient concepts of ether too. I mean, even if we're discounting ether, there's been other concepts of ether within intellectual history. So, I think I'm not an expert on Aristotelian science, but I think it was considered in that context a more subtle manifestation of something more subtle than air.
Mm-hmm.
Yeah, so what ether could refer to in different intellectual frameworks is an interesting question.
Yeah, I think what was being tested, I think in the late 1800s, early 1900s, the Michelson-Morley experiment
Exactly.
was testing a specific definition of ether in physics, and that it's
Which
not
didn't
same.
work.
What's that?
Which didn't work.
Did not work, no.
Yeah.
But that was kind of a substance.
Yes,
like a
He
fluid.
disproved what was considered a scientific theory for some ethereal substance. It was their theory of ether that he allegedly disproved.
Yeah.
Within the context of the experiment and what was happening in the sciences.
That's right.
And could ether be the field of activity?
Well, the field. Well, again, in the third canto, the essential quality of, again, if you use the word ether, I think it's better just say space, because that's what it really means. But the essential quality of space is that it contains things. It actually chidra dhaturtvam. It's the giver of space to things so they have a place to exist.
Yeah.
So, for example, let's say there's certain space between these two walls. So even if, let's say, you sucked all the air, so there was literally, let's say you created a vacuum between these two walls, you can still measure the distance.
Yeah.
So it's something which is measurable, but it again and again, it doesn't interact with anything. So therefore, it's not like the historical Western ethers.
Exactly.
It's just space. It just means space.
That's interesting, because that is different than Einstein's view of matter and space very much interacting.
Right.
And space itself, a vacuum, has its own. It has energy to it. It's not nothing.
Well, it's interesting because it says Chintan that it gives an opening for things like where they can be. Like, it's like you have to have enough space for something to be in space. And that gets into another interesting thing, like you're talking about the Big Bang and like what exists pre-Big Bang. And so pre-Big Bang, according to the Bhagavatam, there's no space.
Right.
There's no place for things to exist.
That's right.
So that would be an interesting topic,
Oh yeah,
just to, because again, it really kind of means space.
yeah,
Because air is different, because Bhumi, Apa, earth, water, air, earth, water, fire, air, space. So it's not any kind of so Kang is not any type of atmosphere. It's just the space itself.
yeah. And that's why Joe Stover at Gonzaga is a
Yes.
great resource because he's a mathematician who studies space, like more abstract space.
So
but-
maybe you could post something and he could weigh in.
yeah.
We might want to pull Joe into our TOVP discussions.
Oh yeah, Joe could give a talk maybe.
For
Yeah,
sure.
yeah.
Yeah.
Joe's good.
Yeah, I mean, what I'm hearing is some kind of more in-depth discussion of Sankhya, really, and
Mm.
Yeah.
because I think Prabhupada's translation ether, most people would translate Akasha as space.
Yeah.
But there's another issue here too. There's the tanmatras, which I've never understood. There's some kind of underlying, and this might be something where you can go with dark matter. I don't know, but you've got this idea that the physical elements out of which things are formed, there's some kind of more fundamental underlying thing called the tanmatras.
As I understand it, the tanmatras are the specific type of perceptibility of each of the gross elements.
But people have been extending that to try and model them as fields, like you would in physics. So yeah, they're hard to understand, but you can try and model them as fields that generate the same way.
Yeah, they're inferred also. That's the other thing. At the very beginning, you said
Yeah.
cosmology is based on sense perception. I disagree, and I think that it's more like Sankhya, which is they kind of take what you see, and then they're trying to infer the existence of other things on the basis of what is perceived. It seems like that's more inference seems to be more, which follows after sense perception, more fundamental, but. Are these tanmatras something like dark matter in the sense that they're necessary for the conditions? They're necessary preconditions for what we see. I
Hmm.
don't know.
Well,
Something maybe.
Murali Gopal has thought about that some bit, and he's actually going to present on something similar to that at the conference. Over my head, we talked about it last week, but I still don't quite get it. Okay. This is what we just talked about. I can move on. So in the Vedic process of creation, there's a sequential unfolding of the elements. From ether involves an alteration of gross material substances and modes of sense perception. Tanmatras, there you go. Therefore, according to the Vedic conception, properties of matter are intimately tied together with the processes of sense perception occurring in conscious living entities. And for physical cosmology, this of course is completely disregarded, and that perhaps the theory of everything requires the existence of a conscious observer. So Sariputta is kind of bringing it all around to the necessity of folding in.
Is that
conscious observer.
the last?
Yeah.
Well, that's teleology. That the idea that the universe is made as an object of perception as much as if someone paints a picture, they're painting it. The real point is not the paint chemistry. The real point is what you actually see, because all the paint chemistry is serving a telos purpose, which is an object that will be perceived by observers. And so the universe is an object which is created as an object of perception.
Yeah.
This is Kant's view too.
Yeah.
Argued that the notion of a perceiver is a necessary. It's the most fundamental necessary precondition for talking about anything. As soon as you talk about something, you're talking about somebody that perceived it. Apperception, we called it. It's necessary. And so
How do you
time
call
and
it?
space. Apperception.
Apperception.
The transcendental condition for there to be anything at all is apperception. And so is time and space. He said that we can't think about this whole issue of what existed before the Big Bang without time and space. Kind of be like it's not even. There's no discussion there. As soon as you think with time and space. There's no ability to think outside of it. Period. He said. So I think
And the Ding on sich, the things in themselves.
yeah, we just don't have access to that.
And then to jump into experimental physics, going back to Young's experiment, the double slit,
Yeah.
then you'll have the controversy. Does it take a conscious observer to collapse the wave function?
Mhm.
And it was just a paper given at the conference in San Diego that Drew DeCarmo was at, and been going on a while. That a conscious observer can impact it. And of course, there's some controversy with that, but the experiments, kind of like the pair experiment in Princeton, seem to indicate, it can, but that of course creates some controversy.
Yeah, I think that is a bit beyond our pay grade.
Yeah,
The observer
that's
effect.
not cosmology.
Yeah, because it's been around for 100 years, and some of the smartest people have been thinking about this, and they're still in the same place.
Yes,
So it's very hard that
Absolutely.
those experiments are befuddling. How much time do I have, man?
as much
Three,
as you like.
4 hours?
We have
Okay.
30 minutes.
Okay, I should be done 10 minutes. So then there's, I believe this is the second to last part, is about the scale of cosmic distance. This is pretty cool. So from the modern cosmology standpoint, this is how we basically do what we do in terms of knowing distances to objects. So the first one for close by distances like stars in the night sky, we measure distances to objects by what's called parallax. So if you want to, you can do this experiment. Just stick your thumb out in front of you and then close your left eye and then close your right eye and then switch back and forth. The position of your thumb moves like this. So if you have the sun here and we're revolving around it, you can view a star from here. You go around 180 degrees, you view it from here. That angle gives you a distance to an object. So that only works up to a point. And then the farther you get away, you have to bring in new ways of figuring these things out, like Cepheid variables. So these are objects in other galaxies that pulse at a certain rate. And from that pulse, it's a pretty simple equation to figure out how bright they are. So their brightness and their dimness tells you about the distance to the galaxies. The farther and farther away you get, the bigger the error gets on how well you understand the distance.
The error.
The error. So if the closer the things are, the more accurately you can measure them. It gets a little bit worse as the farther you go. And then further galaxies, since now we can get observations of hundreds of thousands, potentially millions of galaxies outside of our own. With that many, you can pick up singular events in each one that happen in, not very often, called supernovae, which is where a massive star collapses and explodes. And that brightness is actually brighter than all the other millions of stars in the galaxy. It's such an incredible event.
There's that one star is brighter than all the other ones.
All the other
together.
stars combined. So some galaxies have 1 trillion stars, and that one explosion outshines them all just from one star. It's that energetic. And that happens, we believe, at a fundamental mass. If it reaches a certain mass, it explodes. And that mass has brightness, an intrinsic brightness. So if you can find these supernovae in different galaxies, you can start to build your cosmic distance ladder.
And do the numbers they use, are they like they're consistent with normal, let's say, equations for figuring out like the brightness and amount of energy that it all works out?
Yeah. They're actually not particularly daunting equations at all. It's just sort of luminosity, mass relationships. You can get a distance. And then for things that are really farther away, we use something called redshift. And this is what we were talking about before, BT, where as the universe expands, the speed of light doesn't slow down, but a light wave will get stretched with space as it grows. Doppler effect, exactly. And that amount of stretching or so can give you an idea of how far away something is. And that's how we basically can tell that the expansion of the universe is accelerating. So this is what's called the cosmic distance ladder. There are other observables you can use, but there are still, decent error bars around a lot of these measurements.
Error bars.
Meaning like you make your measurement, but there's some uncertainty in how good that measurement is. Farther away it is, the more uncertain your measurement. Okay, so now we're left with a few conundrums here. In the Vedic universe, the scales do not seem to match up with modern cosmology. The inner globe of this particular universe is described as being far too small to accommodate everything we can observe in the night sky. It is not possible to even fit even the solar system within a 2 billion mile radius, what to speak of stars and distant galaxies. This is quoting Sadhgupta. Thus, if what we can see must indeed lie within the earthly or even the fiery shell of the universe, then the Vedic account is seriously contradicted by modern observations. Now, how can this be? Well, here are some insights that he has. So the rate of passage of time is much slower, for example, on Satyaloka than it is on the Earth. There might also be a comparable transformation of space in the region of Satyaloka. Thus, while a yogi traveling to Satyaloka may experience that he is crossing 2 billion miles, from our point of view, that could be a much larger distance, going back to this sort of relative perspective view. We therefore suggest that when the Vedic literature speaks of distance of 2 billion miles to the shell of the universe, it's referring to the distance as it would be perceived by the demigods, yogis, and rishis who can actually make this trip. As one passes from covering to covering, the nature of material manifestation is progressively transformed until finally one emerges into a purely spiritual realm. Thus, it would not be surprising if transformations in material energy and its laws of operation were to occur as one approached this first universal shell. He's talked about this in many places. So I'm not saying this solves the conundrum, but it's an interesting insight into how perception can change actual sizes. Yeah.
Would that be related at all to what you just said? That as, let's say, the expansion of the universe accelerates, that light waves elongate, would that have any relevance to relative notions of speed?
I don't think so in the example he's giving, no. I'll think about it more, but not at first glance. I don't think so. Yeah.
Something I've always been curious about, and when we read distances in the Bhagavatam, how confident are we in how we correspond those distances to modern measurements?
Prashni, you want to take that?
I'd like to refer everybody to an article we have posted. If you go to research on the DI website, you'll see an article given by Vasil Semenov, who's our Dvija Govinda, who is discussing this very issue. And what he does is the very thing that you just said. He takes lifetimes that we get from the Vedas of the demigods in the different lokas and does an inversal proportional ratio of how they would perceive distance. And it's really quite extraordinary.
Yeah,
Could you send that to us, Larry?
It's I could. It's right on the website. Yeah, I'll send you a link. It's right posted on the
About the
website.
yojana, the length of the yojana issue, is it?
Yes, it's and so you're looking at the and this was done, and you might know Kalevaram. Steve D was just doing some research on him way back in the 17th century.
Yeah, same thing.
Yeah, was considering the yojana as
Chief astronomer.
yeah. So he was considering the yojana as a sliding scale even back then.
Right.
This is something that a physicist will do very naturally.
And this fits very well with the Einstein time dilation.
Exactly. Yes.
Einstein is predicting
Right.
that's how we should look at it.
So the nature of time shifts as the lifetime
It's
of
a
the person
different
in it.
mechanism, but
It's a different mechanism, but it has some correlation, doesn't it?
Oh yeah.
Yeah, I mean, to explain it real simple, if Doug would go to the International Space Station, we both have atomic watches that are identically synced. You say Simonizer watches, anyway, identically synced. Then when he comes back after a year, his watch and my watch will have different times.
Yeah.
You just prove it.
Yeah, you mentioned that you were talking about, let's say, Deva lokas, Deva worlds. I try to use the word Deva instead of demigod because the word demigod in the English dictionary actually means something else. A demigod is like Arjuna, where one of your parents is celestial and one of your parents is earthly. But you mentioned that time slows down on higher worlds, say like Devalokas. And so that being the case, I mean, clearly it doesn't mean sort of in a crude sense that they think they're moving normally, but they're really moving very slowly or something. I mean, so time dilation, I mean, do you have any idea what would it mean? Like what you said, that let's say on higher worlds, time slows down, and yet assuming that those people perceive themselves as just moving normally the way we do. So how should I understand that?
Oh man, Interstellar.
Yeah, Interstellar. If you want some good Maya, see the movie Interstellar. It's great.
Oh, really?
Oh yeah, Interstellar is a great movie, and it deals with this exact issue.
You're definitely the authority on those kinds of.
It is quite good, and one of the producers is probably the best mind in gravity since Einstein. That's his thing.
It's a movie, Interstellar. You find
Consultant.
I'm looking now.
Movie night. It's a movie at night.
It's really good.
Yeah, movie night.
Yeah.
Let's do movie night.
Yeah.
No, seriously.
Seriously. I mean,
Yeah.
Alila, let's schedule a movie night, please.
No, science fiction movie night. This is BI.
Yeah, Marge is like the whole premise. This guy basically goes and has to do this voyage and comes back, and his daughter is an old woman and he hasn't aged.
There's an identical story where someone
Yeah.
goes to a higher world and comes back. Several generations of his family have already died.
Exactly.
And there's no recollection of anybody.
Yeah.
That
Yeah, cool.
So, yeah, I mean, this is,
And Muchikunda.
and yes, and
Yeah.
Could you just quickly go back to one of the previous slides?
Which one?
No, the one.
Oh,
just previous.
shower.
Yeah, that one.
Shower. Okay.
So you were saying there that beyond the universal shell, that it's then you're in like a completely spiritual. Yeah, purely spiritual realm. So when we were discussing, we had a group for discussing what the meaning of Brahmanda, what a Brahmanda is.
Yeah.
And not that we necessarily are correct, but it seems that most of the time it can be used in different ways in the Bhagavatam. Sometimes more like what Western astronomy considers to be the universe, but most of the time it seems to refer to the solar system.
Yeah.
So if that was the case, so if would that mean that interstellar space is actually the Brahmajyoti, the spiritual realm? Is that would be, to me, that would be a logical.
Well,
conclusion
yeah,
from
unfortunately,
that
that's going to be another great talk at the November workshop. What is Brahmanda? I think Dweja go.
Yeah, it's yeah.
Is the ecliptic oval?
Is it oval?
No.
No.
Because Brahmanda or Jagadanda, the word anda literally means egg.
Yeah.
But it also means an oval shape. So we have to look, is the galaxy oval?
Oh.
Well,
Is anything out there?
that's a
oval?
that's a fun
solar
question.
system is over.
Don't say the universe.
Bhupal.
Yeah.
Well, if you
Bhupal
say it,
gave-
define what you
just
mean by it.
edited his transcripts, the talk he gave at Cosmo 3. And there is evidence for a ellipsoidal universe.
Well,
It's very slight.
It's not evidence. It's in the realm of possibility.
Okay.
Among possibilities. It's not ruled out.
Is
No.
evidence that it's within the realm of possibility.
Yes. How's that?
He's a professor of astrophysics
We'll
at
take a look
Washington,
again.
at Washington University.
Oh,
So he's
really?
authoritative, yeah.
But I will say,
He's disciple of, I won't,
Washington University, St. Louis.
yeah.
yeah.
No,
It's a very good school.
We,
yeah, it's an excellent talk.
So we
See it published. soon.
not too technical, but we model dark matter in the universe, like how it evolves through cosmic time. And galaxies are thought to form inside big clumps of dark matter.
Whoa.
So these are called dark matter halos.
Oh my God.
So you know how the ratio I was showing you of dark matter to visible matter, that kind of holds true for an individual galaxy. There's a galaxy at the center, and there's this big halo around it of dark matter.
So the halo is
Holding
much
it
bigger
together.
than
Much
the
bigger,
center.
much bigger, volume wise.
Oh,
And
layers.
those are generally ellipsoidal.
It's just that little chewy
Yeah.
center.
The layers around the galaxy
Well, the dark matter
Yeah, yeah.
around it is
Generally,
often like a
Like that.
oil shape.
Is that a consensus view or just one idea of what it might be?
No, basically you can just run any cosmological simulation and measure the amount of bound dark
So
matter.
the dark matter halo, is that widely accepted?
Yeah, I hope so. That was my whole thesis. So. Fingers crossed. But yeah, they're generally not spherical. Yeah.
Not spherical.
I don't know if this is a silly question, but what's the Vedic thought on time travel? Is that a real thing? Is that a farce?
last paper that Sadhguru ever published in the back guide was on that issue. If you give me your email address, I'll give you.
Me too.
Yeah,
Yeah,
please.
sure. I
Yeah,
remember that.
remember that
What
one?
was
Yeah,
his, what was his
2007.
brief
Time travel.
thesis?
His basic conclusion was that no,
Yes, Hollywood, not.
yeah, there's
Not
not.
Wait,
Vedic Cosmology.
wasn't it,
Certainly
there's
not.
evidence,
Yeah, no reverse time travel.
there's evidence of so-called going into a future, but you can't go to the past and then return to whatever the present is.
But as far as the future, the word for future in Sanskrit,
That's another big issue.
yeah, the word for future is bhavisha, which means that it will be, which is what they say also in German, Zukunft, that which is to come,
Yes.
or avenir in the Latin language.
So it
is
doesn't
to come.
exist.
Yeah,
It's not
so it's
there.
something that will be but doesn't exist now.
But there's example, I mean, so it's how we're using these terms, they go
Right.
to, but, one thought that came to me is in classical physics, time is absolute. And isn't anymore in science.
Yeah.
So like when we're saying to the future, to the back, you're getting into ethereal territory, so.
Although, for example, that famous story of Kukudmi,
Yeah,
where he comes back and generations of his family are all
Yeah.
gone. Some people will probably be happy about that. But anyway, so he comes back. He comes back, and it's not that. In other words, there's no hint that he could go back to the time he left. It's really gone. And the word for past, if you look at the Sanskrit word for past and future, the word for past is atita, which Krishna uses several times in the Gita, which means literally, which is gone beyond. In other words, it's gone. It's gone, and the word for present, I think the Sanskrit words really explain the conception. The word for present is vartamana, the word Krishna uses, which means existing. It's a present participle. That which is functioning or that which is literally going on now, and that which is already past, it's already gone, is atita, the past, and the future is bhavisha, that which will be.
Things do get complicated in physics if there is something that defies all of this and can travel faster than the speed of light.
I was going to ask you about that. I've heard some people say that, what do they call that spooky action at a distance where the
Entanglement.
entanglement, and some people interpret that to mean, like, possibly, it's obviously just conjectural, that somehow these particles seem to be communicating faster than the speed of light.
No, that's generally not accepted.
Yeah, that's.
How's that answered? What's the response to that?
Well, I'm not an expert in it, and it's quite complicated.
That's a really Gopal question.
It is.
Okay. I'll ask him.
But it's a good one, and it's important to know when people ask about that sort of, because the conception is that you take two things, separate them across the universe, one changes its spin or position, and the other one automatically. How does it know?
But there's no information being
There's no
communicated,
information
how it's
communicated.
answered.
So yeah, there's no.
So strings.
Not a satisfying answer. But I wonder if saying that doesn't affect the speed of time. It's just sort of like what Thomas Kuhn talks about, like, defend the paradigm as opposed to really being open to other possibilities.
Mhm. Yeah.
I'd like to make my usual plug for computers and video games. Seeing your slide about the underlying axioms, right? The underlying assumptions, and then listening to BT talk about the observation stuff and like how, this is like a little bit beyond our pay grade, that reminded me of, the simulation hypothesis and this idea of conditional rendering, right? So conditional rendering is this idea in simulation or video games where you have an underlying information state, but that's only kind of manifested, it's only computed, it only like becomes visible to the observer when the observer is like looking in that direction or interacting in that direction. So you have a virtual world, you put on like a VR headset, and that whole world is informationally there underlyingly in the code. But only when you are looking in a certain direction or interacting with a certain thing does that part of the code actually become rendered. The numbers get all crunched by the computer, and then it kind of like it shows you, the pixels or the sounds or the haptics or whatever. So so for me, the interesting innovation that we have now in terms of in terms of thinking about how observation affects things is computer science and virtual reality, right? Because we have developed so far in our models of what we can actually create with this underlying computational assumption that there is this information state and then something is rendered from it. So that's why I think that like this is a big reason why, maybe the main reason why I think computer science and virtual reality and video games are so important to this endeavor, is because if you have this underlying assumption that is the computer science assumption, and proceed from that, then you can explain a lot of these things like entanglement in a much more intuitive and accessible way.
Yeah.
Interesting, very interesting.
I totally agree. And
Doug actually recommended that book to me.
I mean, some people, I've heard this argument. So you often do this rendering because it's much more efficient for a computer to not have everything
Define
existing.
rendering
Well, so like,
for the elderly.
so like over here, there's nothing there. I'm not looking at it. So for a computer, it doesn't make sense to use all that computing power to have that created already. When I look at it, it's generated. And it's a very effective way.
So your looking tells the computer to manifest something.
Yes, and a lot of philosophers have taken this very seriously and been like, well, the moon isn't there if I'm not looking at it. Reality only exists when we observe it. And I don't know how far one would want to take that. But it is, I have heard it's an argument, a common argument that is that from physicalists is that why would God create a universe that took so long for life to observe it and have so much empty vastness that's doing nothing and so much waste of space? Seems wildly inefficient. And
there's all kinds of philosophical assumptions.
Oh, I know. But this is a new retort to that, which is that
that's from medieval times too.
Yeah, that it's not like that. It's not rendered until you observe it. It's not inefficient. That's just one response.
Yeah, so that's why I'm saying there's a development now.
Yeah. I would say one word of caution, and that is what history shows. The history of, well, just say history, is that there's a very strong pattern where whatever is the current state of technology or science, applied science, in a particular age, everything is analogized to that.
Yeah.
So, for example, during the early Industrial Revolution, everything was explained in terms of just sort of gross mechanics. And then there was a time when everything was explained in terms of telephones and so now that we're doing, it doesn't mean the analogy has no value. I think what Christina said, I think that there is a real analogy.
Yeah.
There is a real analogy and we can learn from it. But just, but we have to be careful not to think that it's sort of an all-encompassing metaphor or analogy, which history shows people tend to go too far with the latest technology.
Well, it's just like science. I mean, science is, we used to think that mice came from straw, like spontaneously generated, and now we're like, no, there's actually, genes and stuff that are involved.
Oh, really? Who thought mice came spontaneously from straw?
I thought.
Oh, okay. Hey, it's like today. It's not like everybody thinks.
I apologize.
Yeah, any. It's a debate.
No, that's a good point, because if you look at large simulations in the universe, it looks like the neural map of the brain, and people say, oh, it's a network, and just like the human brain, so the universe is a giant brain. It's just the technology of the time.
Since I'm prone not to shut up. It's not just science, it's whatever's like dominant within a culture, that's the shared reference points. But if you're going to have a discussion, these are the This is what we'd use as a common lingua franca.
There is an evolution, so there is something new and only
Evolution,
valuable
there's always
Yeah,
change.
to be gained from the
definitely.
new stuff.
Yeah, definitely.
I'm gonna jump in here. We only have 8 minutes
Okay.
left. I think we need to get in and just talk, and then we can all stay and
I think
talk
I have,
forever.
I think I have one more subtopic. Yeah, the nature of stars, and that's it. This won't
Okay.
take too long. Okay, so from an astrophysics point of view, this is another, I would say, wildly successful field. Still with its shortcomings, but astounding what we know, and what we can predict, and then go out and observe and match those theoretical predictions. So in the life cycle of a star, and keep in mind, astrophysics, where it just comes to stellar astrophysics, is incredibly complicated. It's got fluid dynamics, atomic physics, nuclear physics, chemistry, gravitational physics. Everything we know in physics and chemistry is in here. It's very complicated. So you basically start from some giant cloud of gas, it's called a nebula, and different pieces of that will fragment under gravity, and they will start to form these what are called protostars. So it's not a full-formed star that's got nuclear fusion going or anything like that. It's in its sort of baby phase. And then as it gets bigger and bigger, and nuclear fusion ignites, and you get sort of a full-blown solar system going, you essentially have two tracks. You have low and medium mass stars, and then high mass stars that kind of form this divide where they take different evolutionary paths. So the lower mass stars and medium mass stars like ours, it's generally thought that its future will be a red giant, and its then destiny will most likely be something where it fizzles off into just sort of a cindering sphere in the sky for trillions of years, perhaps. With higher mass stars, they can go a lot of different routes, where you can have them get as the supernova phase I talked about, and certain mass stars aren't quite big enough to form black holes. The smaller mass ones form what are called neutron stars, and then the higher mass ones, their life cycle then becomes a black hole. And the inside of stars are incredibly fascinating. It involves what I'm showing here is called the proton-proton chain. It's how we synthesize and make heavier elements. The idea being that the explosion of said stars is where basically is what infused the universe with all the elements that make life. So here's the provocative ending from Sadhuhuta that I like, and just allow me to read this. Prabhupada has repeatedly compared the stars, we all know this part, to reflecting planets or moons. His reasoning is presented in the purport to the verse in Bhagavad Gita where Krishna states, "Amongst the stars, I am the moon." Prabhupada says, "It appears from this verse that the moon is one of the stars, therefore the stars that twinkle in the sky also reflect the light of the sun. The theory that there are many suns within the universe is not accepted by Vedic literature. The sun is one, and as by the reflection of the sun the moon illuminates, so also do the stars. Since the Gita indicates herein that the moon is one of the stars, the twinkling stars are not suns, but are similar to the moon." And
Just
yeah.
one problem with that logic, obvious problem. The Sanskrit in the Gita is Nakshatra Namaham Shashi of the nakshatras. I am Shashi, the moon. And so I'm not an astrologer, but I understand that somehow the moon, the nakshatra, somehow the moon has an important role in your life. So it doesn't mean that the moon is a nakshatra. It just means that I am like the dominant power that somehow influences the nakshatras. So the logic here is very tenuous.
Well, Prabhupada does qualify it with it appears.
Right. So therefore, he's not claiming it's an absolute truth, and
Appears.
and then the theory that also Prabhupada says that we just on VAST we got today.
Yeah.
That's a cold, but and I made the point
Flames
that
on the moon.
that why is there a dark side of the moon? If the moon is self-luminous, or there's flames on the moon, then how could you have a dark side of it? So I think I mean, Prabhupada taught us very clearly that when he's not directly quoting Shastra, it's just, speculation.
Yeah.
So for philosophical, what do you call philosophical speculation, where you accept the Shastra statements as true, but you try to interpret them. So I think this is an example of accepting Shastra, but then trying to interpret it. And even the acharyas disagree, as argue about. So this is not an area of absolute truth like Krishna's God or the soul is eternal.
And I might add, in the 15th chapter of the Gita, Prabhupada talks about many suns.
Yeah,
That one?
there's
15,
there's
12.
nothing absolute about the material energy in one sense.
I don't remember.
Yeah.
I think it's 1512, but
Yeah,
let
that's
me
that's
see.
what I have quoted here.
So
Is
it's
this it up on that screen?
This that I have up here.
Yeah.
Yeah, it's
Because
taken-
actually the Gita doesn't directly say that.
Excuse me, we only have 1 minute
Should I-
left.
Okay.
2 minutes?
Well, my next
Well,
one
you could
is
probably
that.
qualify
Thank you.
Prabhupada's comments
Yeah.
on 15.
Yeah.
I'm done.
Oh, yeah, perfect,
But
okay.
you're unvast, aren't you?
I
Suppose
sort
it
of.
is unvast today. What the Gita actually says that this one sun illumines the whole loka, which means world, planet, which could just mean the earth. So all the arguments for there only being one sun are extremely speculative and often not based on a necessary meaning of the Sanskrit word.
Let me add 1512. From this verse, we can understand the sun is illuminating the whole solar system. There are different universes in solar system, and there are different suns, moons, planets, etc.
Yeah,
Well, that would become a different
Every
universe.
Every
And
universe
each
has
universe
itself.
has one
Yeah.
sun.
Every universe has
Well,
one sun.
right here, he said it.
But I said
In
there
this
are different.
commentary.
They said there are different universes and solar systems.
Well,
Yeah.
but you could take him to
Yeah,
mean that
I
in each universe there are solar systems.
Yes,
Yeah,
yes.
You could take it to
You
mean
could say
that.
that.
It's just that the Sanskrit word is not really saying that directly. The word loka, it's just not, that's not the main meaning, universe. It's like you say the whole world, he's got the whole world in his hands. It could mean the universe, but you just say like he's world famous. It doesn't mean that it's all the universe.
Yeah.
Okay, thank you very much for your attendance. Thank you, Doug, for sharing that wonderful summary. And to all of you online, thank you very much. Please join us in 2 weeks, Saturday, October 7th. We're going to go into Chapter 7 of Vedic Cosmography and Astronomy, Redshifts and the Expanding Universe. It's going to be presented by Hugo Stetz, who's here with us today. Can't see. Oh, yeah, I see you right there. So Hugo has received a BS in Aerospace Engineering Sciences from the University of Colorado in 2021. He serves as a commissioned officer in the United States Navy, is a qualified nuclear operator, and has been practicing bhakti yoga for over 3 years. His many interests include exploring how the modern scientific worldview can be supplemented and refined through the application of spiritual principles. So we look forward to hearing from Hugo in 2 weeks. And for the recordings for this session and past lectures, please visit our YouTube channel, Bhaktivedanta Institute for Higher Studies. Thank you very much. Hare Krishna.
Thank you.